Determine for the function g of x equals x plus 4 for x is less than 2, 2x squared minus x for x is greater than or equal to or less than 3, and 7x minus x squared for x is greater than or equal to 3. At each of the x coordinates, x equals 2 and x equals 3, whether it is parts a through e. Parts a through e here involve the continuity of the functions, so the first thing to do is write down the definition of what it means to be continuous. And that's limit as x approaches a from both sides of g of x equals g of a. Specific to this problem, we're looking at the x-coordinate of 2 and 3, so we can write each of these down for 2 and 3. Limit as x approaches to 2 from both sides of g of x equals g of 2, and limit as x approaches 3 from both sides of g of x equals g of 3. Now we do not know if either of these are true yet, so we'll put question marks above them, but if they are true, it is continuous at each of those x coordinates. The first thing to do is look at the limit as x approaches 2 from both sides of g of x. G of x is a split expression function, and it's splitting right at the x-coordinate of 2. And therefore, the two-sided limit will be determined by the results of the two one-sided limits. So we will want to look at the limit as x approaches 2 from the left side, indicated by that negative superscript on the 2 of g of x, and limit as x approaches 2 from the right side, indicated by the positive superscript on the 2 of g of x. Let's start with the left-sided limit. Left side of 2 means less than 2. And that means we will replace g of x with x plus 4 in the split expression function. Next thing to do is try plugging a 2 in for each of the x's, and that'll give us 2 plus 4, which is not the 0 over 0 indeterminate form. It's determinate, and it's coming out to a 6. Now we will look at the right-sided limit. The right side of 2 means greater than 2, but this is a limit. It's approaching. You want to stay close to 2. So you don't want to be greater than 3. You want to be greater than 2, but less than 3. You want to be near 2, but still greater than it. So we will replace g of x with that expression of 2x squared minus x. The next thing to do is try plugging a 2 in for each of the x's. That'll give us 2 times 2 squared minus 2. 2 squared is a 4. 2 times 4 is an 8, and then minus the 2, and 8 minus 2 comes out to a 6. The two-sided limit is determined by the results of the two one-sided limits. They match. They're both a 6. Therefore, the two-sided limit is a 6. We also want to evaluate g right at 2. And it's a split expression function. That's where it includes 2, which is right here where x is able to equal 2. We use that expression. And so we will have 2 times 2 squared minus 2. 2 squared is a 4. And 2 times 4 is an 8 minus 2, which comes out to a 6. So to recap for g of x at 2, we have the limit as x approaches 2 from the left of g of x does equal the limit as x approaches 2 from the right of g of x, and it does also equal g of 2, and that's situation A, which is continuous. At least at the x-coordinate of 2. Now we want to look at the x-coordinate of 3, so we'll start with the two-sided limit x approaches 3 of g of x. Since g of x is a split expression function that is splitting also at 3, we'll have to work out each of the one-sided limits separately to determine the two-sided limits. So we'll have the limit as x approaches 3 from the left side, and limit as x approaches 3 from the right side of g of x. And we will start with the left-sided limit. The left side of 3 means less than 3, but we want to stay near 3, so we don't want to be less than 2. That's too far away. We want this one. And so we can replace g of x with 2x squared minus x. And that will give us, if we plug 3 in for each of the x's, 2 times 3 squared minus 3. 3 squared is 9. And 2 times 9 is 18. So 18 minus 3, which comes out to a 15. Now we will look at the right-sided limit. The right side of 3 means greater than 3, and that means we'll use this in the split expression function. So we can replace g of x with 7 times x minus x squared. And that will give us 7 times 3 minus 3 squared, if we plug a 3 in for each of the x's. 7 times 3 is 21, minus, and 3 squared is a 9. And 21 minus 9 comes out to 12. Since the results of the one-sided limits do not match each other, the two-sided limit at 3 does not exist. And this means we will have a jump discontinuity there. Now we want to determine whether it's continuous from the left side, right side, or neither side, and that's going to be determined by g of 3. G of 3, if we look at the split expression function, that's where it's equal to 3, and that's there. So we will make use of that expression, plugging 3 in for it. So 7 times 3 minus 3 squared. 7 times 3 is 21, minus, and 3 squared is a 9. 21 minus 9 is a 12. So we have the limit as x approaches 3 from the left side of g of x does not equal limit as x approaches 3 from the right side of g of x, but that one does equal g of 3, and therefore we would have it, because it matches the right side limit for g of 3, it's going to be continuous from the right side, but because the left side limit and the right side limit do not match, it's a jump discontinuous. So we go with situation D, and that's going to be jump discontinuous, but continuous from the right side for our x coordinate of 3.